All right, how's it going, y'all? And welcome to my channel. This is a channel for educational purposes. We try to look at um, some of the theories of everything that have influenced my life, and also, uh, so-called crackpots uh, who spent their whole life working on their magnum opus and only to put out some kind of masterpiece that gets completely ignored or never heard of in the first place or even ridiculed. And I still think it's a great thing, so I'm trying to get it out there. And we look at all other kinds of all-encompassing theories. But for the last many, many months, we've been focused on Dewey B. Larson and his reciprocal system of theory. Today is our 355th video on the reciprocal system. And the basic idea behind the reciprocal system is that we do not live in a universe of matter, and we don't live in a universe of energy or force or anything else, but we live in a universe of motion. And motion for Larson was the relationship between space and time. Now, originally, when he first pulled together his two fundamental postulates in the late 1950s, he said that the universe was made out of space-time. He eventually changed that to motion, and motion is the relationship between space and time. Later in his life, he actually said that by motion, he was really meaning change in 3 dimensions. And I think some of that is related to, our understanding of motion. In the sense that Larson means, he's talking about what you call a scalar motion. Scalar motion is different than your basic, velocity or other kinds of motion that has units attached to it. A scalar motion is a motion that has a magnitude, but it has no specific direction. And the general model that you use to visualize this is using a balloon with dots on it. As you blow up the balloon, all of the dots are moving away from one another, but in no specific direction, or really every direction. All of the dots are moving away from all the other dots. And in fact, even the spaces between the dots are moving away from each other. So everything on that surface of the balloon is moving away from everything else. And in fact, you can extend that analogy or that visualization to another dimension by, using something like raisin bread, where when you cook the bread, it rises, all of the raisins, even in the interior, are moving away from each other as well. So that's what you think when you're thinking of a scalar motion, a motion with a magnitude but no direction. You can also use a clock. Larson uses the term, in fact, clock time and clock space. Clock time, the clock is always getting later and later and later and later. But it's not getting later in any specific direction. It's just getting later. And in clock space, the space is always getting farther and farther and farther apart, but in no specific direction. So that is kind of the first prong of Larson's first postulate. He had 2 fundamental postulates. And he took these 2 postulates from the late 50s, and then from those 2 postulates, he derived a theoretical universe of what the universe would look like if these 2 postulates were in effect, and determined then in his books that the postulates dictated a theoretical universe that looks quite a bit the same as the Newtonian universe, that all of the scientists pretty much assumed was true, except for in these relativistic situations of the very fast, the very small, and the very large, that had to be kind of revised by Einstein and his generation in the early 20th century. And they came up with all kinds of things to kind of repair the Newtonian universe for these extreme situations. And Larson came up with pretty much the same finding, that the Newtonian universe is what his postulates dictated, except in the relativistic areas, the very small, the very large, and the very fast. And in those cases, he had different concepts, and in some cases, different mathematics than what the Einsteinians and the quantum mechanists and those people had come up with, a generation or two before Larson came around. And I find that Larson definitely eclipses the accomplishments of those people, because his solutions work. He's able to predict results. He's able to predict new phenomena, such as quasars, that had not been discovered before he predicted their existence, and their existence in great detail. And but most specifically, Larson's concepts make sense. It's not like Heisenberg or Einstein that they're just coming up with stuff, and they're even saying, oh, well, this really has no meaning in reality. It's just a mathematical, model. This, electron or whatever. You don't think of this as being literally something that's actually happening. This is just something that we're using for convenience to make calculations. Well, Larson's not doing that. He's giving you the concepts. He's telling you why these things happen. They are consistent with his theory. So that's one of the main reasons that I like the reciprocal system. Now, it's not perfect, and Larson was fallible, made some mistakes, and I think that a lot of those mistakes have been corrected by a few of his revisers that came to the fore in the later years of Larson's life and after his death in 1990. But going back to his fundamental postulates, the first prong, as we were saying, is the clock time and the clock space. Then there is also what he calls coordinate space and coordinate time. This is the three-dimensionality, coordinate X, Y, Z coordinates. We generally think of space in that way, of X, Y, and Z coordinates, volume. And time also, under the proper circumstances, has a three-dimensionality, and that is what Larson calls coordinate time. And forgetting what I was just going to say about that. But the three-dimensionality of the reciprocal system is something that is rejected again by legacy science in terms of the time aspect. Time is normally seen as being just a one-dimensional phenomena by your average legacy scientist. Then the third prong is what Larson calls the discrete unit postulate. Space and time both come only in discrete units. You have to have a full unit of space and a full unit of time before you have anything. If you don't have a full unit, you've got nothing. So those units are extremely small. The unit of space is 4.56 times 10 to the minus 8 meters, approximately 1/500,000th of an inch. And then the unit of time is the incredibly small 1.52 times 10 to the minus 16 seconds. That is, over 6 quadrillion of them per second. That's 6 trillion billion of them per second. And so you're kind of thinking these are quantized. These are separate frames. So the universe is more like a cartooniverse, where it looks like we have some kind of continuity, some kind of a continuous motion, but really we have one frame after another, after another, after another, after another, that are very similar to each other, but they are separate, discrete, and they're flashing before us so fast that we can't. We can not even determine, the lack of continuity of a cartoon going at whatever 20 or 30 per second. This is, trillions or even quadrillions, almost a quadrillion times faster than that, or a third of a quadrillion times faster than that. So, of course we wouldn't be able to detect that. But anyway, if we have exactly 1 unit of space in 1 unit of time, then we have the speed of light. The speed of light is 1 unit of space in 1 unit of time. Speed is space over time. All speed. All of our units in scientific units can be expressed exclusively in terms of time and space. They're all relationships, fractions in general, of space over time or time over space. And again, we have this coordinateness of space and time. So both of those time or space components can have multiple dimensions. So you've got your speed, space over time. The car is moving 10 miles per hour, 10 miles of space in 1 hour of time. Energy, time over space. It took me 3 hours to push that thing a half a mile. That's 3 hours of time in 1 hour of space, time over space. Then you also have acceleration. I dropped the ball out the window and it fell at 32 feet per second. 32 feet of space in 1 second squared. And so on and so forth. And so speed in this configuration is 1 unit of space in 1 unit of time. That is the speed of light. That's what Larson calls unit speed. 1 over 1 equals 1. And that unit speed is really the background of this universe of motion. This is the omnipresent, always existing, what Larson calls progression of the natural reference system. Now, we generally only perceive that progression of the natural reference system in terms of time. We perceive the flow of time always getting later and later and later, but the flow of space always getting farther and farther and farther apart is generally nullified by the fact that we are situated within a so-called gravitational field. And so gravity nullifies the spatial progression from our vantage point. So we're seeing, because we reside in what Larson calls the material sector. And the material sector is the slower than the speed of light sector. The speed of light is the boundary, whereas Einstein says that the speed of light is the speed limit of the universe. Larson says that the speed of light is the boundary of the universe, and that half of the universe is moving faster than the speed of light, the cosmic sector, and half the universe is moving slower than the speed of light, the material sector. We reside within the material sector, so we're not seeing the universe from a kind of impartial viewpoint. We are seeing it from one side of the equation. And that's why we see time in its scalar aspect, but we see space in its coordinate aspect. If we were in the cosmic sector, we would see space in its scalar aspect, and we would see the progression of space. Space is always getting farther and farther and farther apart. But we would see time in its coordinate aspect, 3 dimensions of time. And we would have great difficulty moving through time in the same way that we have, resistance and difficulty moving through space. Okay. So from there, Larson wrote his books and wrote books on physics, astrophysics, chemistry, astronomy, metaphysics, economics, and some other topics with articles and interviews and talks that he gave, and then passed away in 1990. Since then, Dr. Bruce Peret has come to the fore, along with Dr. KVK Nehru, and have proposed this thing called RS2, the second reevaluation of the reciprocal system, our reciprocal system 2. And today we're looking at an article that was written by Dr. Peret that's called RS2-106, which is called Dimensions and Displacements. Now, we're at the tail end of this article, so if you wanted to hear the article from the start, you want to go back 3 episodes. This is the 4th episode on this particular article, and we should finish it here today. Now, he's talked about the dimensional situation and, the difference between scalar motion and vectorial motion, and also the difference between spatial dimensions and scalar dimensions. Now, it requires 3 dimensions of space to describe 1 dimension of scalar motion. We, in general, are only able to experience 1 dimension of scalar motion, but there are 3 of them. So we are very much limited in our view, again, of the entire universe. We can only see 1 dimension of scalar motion at a time. And then he started talking about displacements. And displacements are, again, where legacy science is saying where they're measuring their speeds from 0, from their state of rest. So if something is moving, it's moving faster or slower than 0. In the reciprocal system, the reference point, the 0 point, the state of rest, is the speed of light outward in all dimensions, in all directions. And so therefore, the measurements are made from that speed of light datum. And that is what Larson and also Peret are calling displacements. You can either be displaced upward or downward from that unit datum. Okay, let's finish this up here. The section is called atomic rotation. Because we are dealing with a three-dimensional universe of motion, Larson's notation for displacements includes three components: a principal magnetic rotation, a subordinate magnetic rotation, and an electric rotation. So this is how Larson is notating his basically his periodic table. His periodic table requires three different numbers to describe each element. Motion for particles and atoms, or notation for particles and atoms, use three displacements to represent displacement in the three scalar dimensions in the A, B, C format. For example, oxygen is 2, 2, -2, which means that the two temporal rotations have a displacement in time of 2 units, coupled with a spatial rotation in the third scalar dimension of 2 units. So when we have a positive displacement, the displacement is in time. And when we have a negative displacement, the displacement is in space. If the displacement is in space, that means it's faster than the speed of light. If it's in time, it means it's slower than the speed of light. So everything in the material sector is going to be primarily a displacement in time, moving slower than the speed of light. But there can be a component of that atom that has a displacement in space, such as oxygen, 2, 2, -2. Now, if an atom is one of the noble gases, then that third number is going to be 0. So the third number is 0 in all cases when you are talking about the noble gases, helium, neon, argon, krypton, xenon, radon. Okay, now displacements can also represent either material sector, 3D space, or cosmic sector, 3D time structures, which Larson rotates with an Larson notates with an M or C prefix, as well as exchanging numbers in parentheses by those without. For example, M 2-2-1 is material fluorine, atomic number 9. C -2-2-1 is cosmic fluorine, also atomic number 9. So if the atom is a cosmic atom, which is what the legacy scientists call antimatter, then it's negative displacements, or displacements in space faster than the speed of light. This seems to be unnecessary, as the parentheses on the two magnetic rotations clearly indicate to which sector the three-dimensional structure belongs. Larson uses the M or C designation with a superscript asterisk to indicate a charged condition that cannot be represented in the displacement notation. So the notation does get used. One final note on atomic displacements. For a particle, the A, B, C notation represents motion in 3 scalar dimensions, minus the displacement of the rotational base. Larson refers to this rotational base as a double rotating system, or Larson refers to this as a double rotating system that Professor KVK Nehru later identified as a solid rotation, such as the rotation of a ball, rather than the rotation of a disk. Particles have single double rotating system, electrons, positrons, protons, and so on. Particles have single double rotating systems, whereas atoms have two double rotating systems. The displacements listed for an atom are the same for each of these double rotating systems within the atomic structure. Okay, that was kind of a mouthful and a lot there, a lot to kind of contemplate. Again, I would just recommend, that is the end of the article. I would just recommend that you kind of let it wash over you. Don't reject anything out of hand. Just hold it in your mind for later consideration. I would recommend that you try to get a holistic view of Larson's entire picture before passing any judgment on it, because taken separately, each kind of prong of Larson's findings might all seem kind of ridiculous, but then when you fit it together all at once, then it does form a holistic picture. And so he is pretty consistent with how he does things, and it's very hard to notice that unless you really study all of his stuff. So I would just recommend that you hold it in your mind for safekeeping until you've been able to be exposed to the whole picture, which you can be on this channel if you watch all these different videos. As far as I know, this is the only channel that is doing any type of in-depth work on Mr. Larson's reciprocal system. So come to me for your, and I don't profess to be an expert on this in any matter. I get very confused about this stuff at times as well, even though I've been studying it for many years. It's not an easy study, but it is doable, and it is a beautiful system, I think, when you finally do kind of see the whole picture. Okay, and now tomorrow we will come back and look at RS2-107, which is called Mass and Gravity. And so stay tuned for that. Come back tomorrow. Thanks for tuning in today, and have a great night.